Hey, Math 3-2. So we're going to continue on with our fourth lesson here, discovering mutual events or probability of mutual events. We're still in probability. But before we do that, let's do a little review question from the previous lesson and from 2 chapters ago. So here we have there are 9 players on a baseball team, all with equal ability, and the coaches decide to randomly choose players to play in the outfield positions. And there's positions here. Okay. So because there are positions, order matters. I'm just going to write that on that side here. Order matters. Okay. And what are the odds in favor? Now looking for odds. What are the odds in favor of the 2 people, Giselle and Joe, to be on the team? Now to do odds, remember when you do odds here, we're going to do the number of favorable outcomes compared to the number of not favorable outcomes. Now, when I add these together, I get everything. I get the whole sample space. Okay, so I'm 100% of everything that we have here. So if I can find out the sample space and how many favorable outcomes, I could probably find out how many non-favorable outcomes there are. So I can just subtract that over. You can see that as we go. So the number of favorable outcomes here is going to be Joe and Giselle being on the outfield. So if I have my 3 outfield positions and I have Giselle, and Joe here. And then for the 3rd position, because I've used these 2 people up here, I only have 7 more people to choose from. So that's one way to do this, right? But that's putting Giselle in the first left field and Joe in the second one, and then whoever's in the right position there. But I can rearrange these 3 people 6 ways. 6 ways, or 3 factorial ways. So there are, if I punch out my calculator here, 6 times 7 ways to do that. There's only 42 ways to rearrange these people. G and J here, they just count as 1. Right? They have to be those people. So 1 times 1 times 7 times 6 gives me 42 ways in favor of them being in the outfield. That's good. We want that. So what I know so far is that it's going to be a 42 on this side, but I have to figure out how many non-favorable outcomes there are. So to do that, I'm going to find out how many ways can I rearrange these 9 players just in the outfield. You notice I'm ignoring the other 7 positions or 6 positions. Because if I included them up here and I included them down here, they would just reduce out. They would just kind of cancel each other out. You could do that, but then you're still going to have to reduce whatever you get as your answer over there. So we have 9 players. We're going to pick 3 of them. There's 504 ways in total to rearrange the 9 people in the outfield. So I'm going to go over here, 504. And then I'm going to reduce this down as much as possible. So I punch in my calculator, go 42 divided by, I don't know if you can see it, 42 divided by 504, go math, enter. This reduces down to 1 to 12 odds in favor. So it's a 1 in 13 percent of probability. Remember, you can add those together to get the total sample space. So 1 in every 13, Joe and Giselle will be in the outfield somewhere. Okay. So let's talk about the next part of this. That was just a review. Let's talk about the next part. So what the very top says is mutually exclusive events. So we're going to do probability of these things. Then what a mutually exclusive event is that when you have 2 or more events that cannot occur at the same time. And to give an example here, if you're standing in one spot, you're only going to see the sun rise and not set at the same time. So these are mutually exclusive events. Events that overlap each other, that have something that could happen at the same time. So maybe you can draw a card. Maybe you're drawing a red card, you're drawing a face card. You could draw a red face card. Those are non-mutually exclusive. So mutually exclusive just means if I draw a card, it's face, or if I draw a card that's not a face, there's no way to get a face card that's not a face card. So this would be mutually exclusive. Now to determine the probability of that, it's actually pretty easy. If you know the probability of happening on one and the probability of happening on the other, the probability of them both happening at the same time would just be the probability of them added together. Okay? Now we can prove that by thinking about what is probability again. So probability is just the number of favorable outcomes divided by the number in the sample space, which in this case is our universal set. So the number in the universal set. Okay, so that's in the universal set. I'm just going to change that to a U for the universal set. Okay, now the union between two things. So imagine this: if these are not crossing over each other, there's nothing in between them, they're not touching each other. If there were like 5 things in this event and there were 6 things in this event, if I just said the union of those 2 boxes, I would be shading both of these boxes. This box, I'd shade that box, I would shade this box. Anywhere they cross over, I'd count all the spaces, but there's nothing in here in between. So overall, it's just whatever A is, the number in A, plus whatever the number in B are. As long as there's no overlap, I could just add the 2 numbers together. If there's overlap, that's the next page here. You'll see what happens. Now, we have a rule for fractions. If I divide by one thing, I could split this up into 2 fractions that have a common denominator. So this is B. So I can split that up into 2 things like that. This U is the universal set U. Now, probability, remember what it says up here, it's just favorable outcomes divided by the sample set, in this case our universal set. So this is the number of A happening divided by the universal set. That's just the probability of A. And then the number of B happening divided by the universal set, which is just the probability of B happening at the same time. So that's where this formula up here comes from. If they are mutually exclusive, they have to be mutually exclusive, then the probability of that would just be probability of A plus the probability of B. You'll see some examples of that in a bit. Now, if they're not mutually exclusive, so like this little Venn diagram here, in this Venn diagram, there's a piece of overlap here, right? So we're overlapping here, so there's something in common. So they're not mutually exclusive, non-mutually exclusive events. The formula gets a little bit trickier. So if I want to do the probability of these 2 things, it's the probability of one plus the probability of the other minus the probability in between. It kind of, you'll see when we do an example of this, how that works. Okay. Why does this work? Like, what's this minus here all about? We did something like this when we solved Venn diagrams before. If I told you what the union was and I told you what these 2 circles were, you would subtract those over to the other side to find out what this middle piece is. So if I knew what the middle piece was and what these 2 circles are, I can just subtract them out to find out what the union was. So that's what this is, non-mutually exclusive event. So you're going to see, we're going to see one later on here on the next page that kind of involves this process. Okay? So let's think about whether or not they are mutually exclusive or not. So Janek and Violetta here are playing a board game. To move on this turn, Janek has to roll either a double or a sum of 7 with a 2 standard dice. Are the events mutually exclusive? And then we're going to determine the probability of moving. So I want to know, what is the probability of moving, which is the probability of rolling doubles, or, which is the union, sum of 7. If they're mutually exclusive, I could just take these 2 numbers, whatever probability they are, and just add them together. Okay? Now, if they're not mutually exclusive, I'm going to have to subtract out a little piece wherever they cross each other. So I'm not like kind of doubling up that number, and you'll see in a couple of situations here. Number 2 here, there might be some overlap. So I'm going to drop my sample space here to do this one. So my sample space, I'm rolling 2 dice. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then we're going to figure out of all these here, how many of them allow him to move. Right. Okay, here's my sample space. So to move, the sum has to be greater than 7. So remember our patterns here. I can go right down the middle here. 7, 7, 7, 7, 7, 7. Or the sum has to be equal to 7, not greater than 7. So those are all my 7s there. There's a bunch of other numbers on either side, but these are all less than 7. These are all greater than 7. And these are all my doubles. 1, 1, 2, 2, 3, 3, 4, 4. 5, 5, and 6, 6. So if I highlight the 2 events, getting a double and getting a sum of 7, what you notice is that there's no overlap here. So these are mutually exclusive events. One doesn't depend on the other. So the probability of rolling a double is 1, 2, 3, 4, 5, 6. So 6 out of 36, I think it is. Yeah, 36 in my sample space. And the probability of we're rolling a double is also 6 out of 36. This is 12 out of 36. They have a common denominator, so you just add them together, and then I can reduce that down to be 1 over 3. Now I could also have done this way, where I said, what's the number of the union between the two, and divided by the number in my sample space. That's what we're doing up here anyway. Now the union would be, add them all together, there's 12 of them. And there's 36 in my sample space. I also got 1/3. So I don't have to have 2 fractions. I could just done it as one step. Okay. Now, according to different rules here, if a player rolls a sum that is greater than 8 or a multiple of 5, they get a bonus points of 100. Right? So I'm going to be using, I'm just going to go up here. I'm going to be using the same sample space. I was thinking maybe I can just select that sample space there. Might as well just redraw it. Nah, maybe not. I'll just go up here. Okay. So I want to know when the sum is greater than 8 or a multiple of 5. So a multiple of 5 is 5. So there's a bunch of 5s right there, or 10. So 5 and 5. It's 10, 10, 10. Okay? Actually, it might be just better if I just redraw this. You're right. 1, 2, 3, 4, 5, 6. 1, 2, 3, 5, 6. I just want to get too confusing with all the green there. Guess I could erase the green, but I won't. Okay. So I can fill out all the sample space here if you want to. So I got 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 11, 10, 10, 9, 9, 9, 8, 8, 8, 7, 7, 7, 7, 7, 6, 6, 6, 5, 5, 5, 4, 4, and 3. Okay. So I got my sample space here, all the sums. Now what I want to know is when are they greater than 8? So greater than 8 would be here, 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 here. All the 9s, the 10s, the 11s, and the 12s. So that's the greater than 8s. Okay. And yeah, okay, good. Just want to make sure that overlaps nicely. And I want to know when. Oh, this is really far back. Oops. I also want to know when you get a multiple of 5. So a multiple of 5 would be 5, 5, 5, 5. Oh, I just erased them. Don't want to erase those 5s next time. Those 4 5s there that were there, and these 10s. And you can see that there's overlap here. It's changed color on us. So this is not a mutually exclusive event. Are these mutually exclusive? No, they're not. The one above it was, all right, because they were separate. what's the probability? So what we're going to do here is we can either use, just by counting what we have on the picture here, the probability of getting a bonus is, we just count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oops. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So there's 14. You notice I didn't count these 10s twice because they're common on the Venn diagram, so why would I? And then my total will be 36. So I get 7 out of 18 here. Okay? I can also use the formula to do this and see if we can get the same thing. So to get the bonus, it's either, you get the problem 5s, let's call that 5s, or, what's the other one? Greater than 8. Greater than 8. Okay? So, what's the probability in 5s? 1, 2, 3, 4, 5, 6, 7. So 7 out of 36 to get the 5s. This is the 5, the mults of 5, I should say. Okay. Then the probability of getting the other ones, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, 10. 10 out of 36. That's for the greater than 8s. Now, we want to subtract out what they have in common because there's 3 of these. By counting these 7, the 7 5s here, and these 10s, I've counted these three twice. So I need to subtract out those 3 because I counted them twice. So I subtract them out. I get 14 over 36 again. So 7 over 18. So it works out. So that's what this little minus is for. The minus is to subtract out what they have in common. So subtract out this yellow piece here, right? Because I don't want to count it twice when I add them together. So I need to get rid of one of them. Okay. To avoid making this video just a bit too long, we're just going to stop that one here, and we're going to do the next 2 pages here in the next part. I'll see you then.